Hey guys, this is the second video in Module 5, picking up from the central limit theorem. I had talked about this slide, so I'm going to move on. The next slide is the t-distribution. So now we're going to talk a little bit about this actual t-distribution. So we can always use the standard normal as an approximation, but in small samples, we have to use the t-distribution. That's because the standard normal distribution, the convergence is not immediate. Pretty much what that means is that the tails of the distribution, the things that we're actually interested in, are too small. So in actuality, we have to make them a little bit bigger to make it more difficult for us to reject the null hypothesis. So in small samples, this this beta hat j minus the true beta hat divided by the standard error is going to be t distributed. But as our n grows, we know that the t distribution is going to approximate or converge to the standard normal. But just for small samples, we have to use the t distribution. And there's no harm in using it forever, because once we get to large distributions or a large sample size, it's no different. So we should just stick with it always. So here's a picture of the t distribution using different sample sizes. So this is the degrees of freedom. You might remember that the degrees of freedom are heavily dependent on your sample sizes. I'm not going to get too far into the degrees of freedom, but R is going to calculate all your t-stats for you. But if you remember correctly, your degrees of freedom are low, meaning that your sample size is low. You're going to have a pretty wide distribution, but as your sample size increases, you're going to approach that normal distribution. So because the t-distribution is more conservative, we're less likely to wrongfully find significance. So it makes it a little bit harder for us, but it makes for better statistics. So R is going to automatically give you these t-stats. You should pretty much notice them in the output. I'll talk about that, I think, at the end. And then lastly, we're going to use our t-stats to get p-values. But whereas in Econ 225, we had to use a table, R is going to generate all of this stuff for us. So if you want to test other null hypotheses, I'll talk about that in a second. But most commonly, again, we just test if it has a significant impact, if for some regressor or some x variable has a significant impact, meaning it's different from 0. So for example, here would be how we would interpret something if the beta j is equal to 0. So in other words, this h sub 0 means that xj has no effect on y after controlling for other regressors. So for example, if we have this regression where we have the rate of loan approvals, we have a percent minority, average income, average wealth, average debt, how would you interpret beta 1 equals 0, meaning this one right here? So as the percent minority increases, this must be maybe for like a county or something like that, or for some bank, right? So as the percent of minority is increasing, if this is 0, it's not going to have any effect on the rate of loan approvals. And if it's positive, that means that it would increase, right? If it's negative, it means it would be decreasing. But if it's 0, or what we're going to call as insignificant, meaning positive but really, really small with a large standard error, and or negative but really, really small with larger standard error, that's all going to be 0. So here's another example of school size and student performance. So our Math 10 is going to be the standardized 10th grade math test score. Tote comp is going to be the average annual teacher compensation, number of staff per 1,000 students, and then the total student enrollment. So the regression is going to yield this right here. And we have our standard errors in parentheses. So for example, the log of total comp is going to be the coefficient is going to be 21, but the standard error is going to be 4.1. So if we do that simple math that we had before, so for example, if I could find it quickly, this right here, where we're always going to test if this is 0, you'll have beta j minus 0 divided by standard error. So we'll have 21 minus 0 divided by 4.1. That's going to be a pretty large to be almost like in the sixes, I think, for the t-stat. And the t-stat of 6 is quite large, especially for a sample size of 408. This is probably going to be significant. So then for this one, this question is, do larger schools have worse performance? You would look at 1.3 times the log, and this would be the standard error. So 1.3 divided by 0.7, that's going to give you a t-stat of about just shy of 2. And R is going to be able to perform that t-test for you and give you some sort of p-value, which you can then compare to your alpha. So that brings us to economic significance versus statistical significance. So statistical significance is pretty easy. We just take our estimate, we divide by our standard error, and if that p-value is small enough or a t-value is large enough, then we say that, yeah, this variable has a legitimate statistical effect or significant effect on the outcome variable, on the y variable. This x variable is impacting y in a significant way. But there's two ways where we can get our t value to be large. We can either have a very, very large beta, or we can have a very, very small standard error. If the standard error is just really small and the beta j is small but not as small, and that t value is still large enough to be significant, well, that's great, but at the same time, it might not be economically meaningful. So for example, if suppose this was a lot smaller and this was a lot smaller, that would mean that, if this was 1, but it was significant, it would mean like a 1% increase in total compensation would lead to a 1% increase on the math score. And you want to think, okay, well, what does it mean? How much money is a 1% increase in total compensation? And how much is 1% increase or a 1 unit increase in the math 10 score, right? We have to think about trade-offs from that. Is like, okay, this is the impact, this is the causal impact, hopefully causal. How do we economically interpret this? Statistically, it's significant, it's great, everything's good, but economically, is it important? And that's kind of what this slide's trying to get at. So we typically say that xj, or the variable you're talking about, is economically significant if beta hat is large and statistically significant. So economically significant is usually twofold. You have to have statistical significance first. Without that, it doesn't mean anything. And you have to have a large enough thing where you can interpret it in a meaningful way and say that it actually has a large impact or something like this. So in this case, this example here, drinking hot tea doubles the risk of esophageal cancer. I think that's cancer of the esophagus with statistical significance. Should you drink hot tea? Well, if it's doubling your risk, that's fine, but it depends on what that baseline risk is. If that baseline risk is 5% and all of a sudden it's doubling it to 10%, that's kind of a big deal. You probably don't want to drink hot tea. But if that risk is super, super small and that doubling is really not that big, then maybe it doesn't actually matter. So sure, it's statistically significant, but is it practical or is it economically significant? That's kind of the question you have to ask. So here are some other types of hypotheses. So for example, you can test are coefficients equal to some number. A lot of times people want to know what's the elasticity of something, right? And you want to know if it's unit elastic. That would mean that the elasticity is equal to 1, meaning a 1% change in X will cause a 1% change in Y. We want to test if that's perfectly equal to 1 or not, right? If it's higher or lower than 1. So what we have to do is, instead of using the t-test where we do beta j minus 0 divided by the standard error, we have to do beta j minus 1 divided by the standard error. And this is really important for a lot of macroeconomic stuff, because typically we want to compare your results to actual numbers, or even, in some micro stuff too. So here is an example. It says, is beta NOx statistically significantly different from 1? And this would be that you would have your value and you want to subtract off 1 from it. So you have this right here, and you want to see if it's statistically different from 1, it should actually be a -1. But that's fine. So pretty much you would just redo this t-test with negative 0.954 minus 1 divided by 0.12, and you'd be able to find a t-test. So if it's different from -1, then it would be a +1, and you would have this really small t-stat, where this might be different from 0, meaning R might tell you it's significant, but if you're comparing it to 1, then it's a different test. So just a reminder, it's kind of like a little bit of a pet peeve, but the language we use with hypothesis testing is we never say we accept the null hypothesis, meaning that beta j equals 0, because we can't actually show that beta j is actually equal to 0. We can just say that it's not equal to 0. And it's a little bit confusing. So in other words, we say we reject the null hypothesis, meaning that this beta is not equal to 0, and we're confident in that. Or we fail to reject, we cannot say that this beta is not equal to 0. So it's almost talking in negatives, which is a little bit confusing, but that's just the way we have to do it to be as precise as possible. So here's some hypothesis testing with multiple coefficients. I'm going to talk about this in the next video, and then I'll finish the slides in that one as well.